Really out there, a state of matter that just seems to ignore the normal rules. Superconductivity.
Right.
Imagine electricity flowing like forever. Zero energy loss. Or materials just poof, pushing magnetic fields away.
Sounds like sci-fi, doesn't it? But it's real physics.
Exactly. And it's baffled scientists, but also fascinated them for, what, over 100 years now?
Easily.
So today we're doing a deep dive into that story, the discovery, the breakthroughs that explain part of it, and, the big mysteries that are still left.
And we'll see how these tiny vibrations inside materials play this surprisingly huge role.
Yeah, the vibrations.
And what's really interesting here, I think, is that it's almost like two different stories playing out.
How so?
Well, first you had this huge success story, a mechanism involving things called phonons. We'll get into those. It just nailed it. For one whole class of superconductors. Solved.
Okay.
But then, boom, a whole new type shows up. Totally different. And that beautiful phonon explanation, it just doesn't cut it. Not even close.
Ah, okay.
So our mission, really, is to unpack both things. That first big win and why we're still searching for answers for the newer stuff.
Got it. So let's start with the basics then. How do we even know something is superconducting? What are the signs?
Right. So when you cool these materials down below a certain temperature, their critical temperature, or TC can.
TCC, right.
Two main things happen. Observable things. The first one is probably the most famous. Zero electrical resistance.
Meaning?
Meaning once you get a current going in a loop of this stuff, it just keeps going and going forever. No battery needed, no energy loss. We call it a persistent current.
Wow. Unlike my phone charger cable, which definitely gets warm.
Exactly. That warmth is resistance.
Yeah.
Electrons bumping around, losing energy, superconductors, none of that.
Okay, zero resistance. What's the second thing?
The second thing is maybe even weirder. It's the Meissner-Ochsenfeld effect, found in 1933.
Meissner effect. Okay.
This is where the material doesn't just let magnetic fields pass through with no resistance. It actively kicks them out.
Kicks them out.
Yeah. Imagine you have a chunk of this material, you cool it down in a magnetic field. A normal, perfect conductor would just trap that field inside when it became perfect.
Okay, makes sense.
But a superconductor, as it crosses that TC, it spontaneously generates currents on its surface. Tiny, resistanceless currents that perfectly cancel the field inside, pushes it right out.
Whoa, so it's like it suddenly develops an allergy to magnetic fields.
That's a good way to put it. And this was huge because it proved superconductivity wasn't just, infinitely good conductivity. It was a fundamentally new state of matter.
Yeah.
A true quantum phase transition.
Okay, that is mind-bending. But hang on, this brings up a problem, doesn't it? Electrons are negatively charged. They repel each other strongly.
The Coulomb repulsion, yeah. It's powerful.
So how on earth do they suddenly start cooperating in this massive collective quantum dance to achieve zero resistance and field expulsion? What could possibly overcome that repulsion? What's the glue?
That was the billion-dollar question for decades. What's the glue?
And the first big clue, the real smoking gun, came when?
1950. That was the discovery of the isotope effect. Really pivotal moments.
Isotope effect.
Yeah, two groups, actually, founded around the same time. Emmanuel Maxwell in the U.S. and another group, Reynolds, Sarin, and others at Rutgers. They were looking at mercury.
Okay, mercury. And isotopes are just different versions of mercury atoms, heavier or lighter.
Exactly. Different numbers of neutrons, so different masses. And what they found was amazing. The critical temperature, TSE, changed depending on which isotope they used.
It depended on the mass of the atoms.
Directly. Heavier mercury isotopes had a lower TC. And it followed a really specific mathematical relationship, like TSE goes as mass to the power of -1/2, roughly.
-1/2. Why is that number significant?
Because physicists already knew something else vibrated in proportion to the inverse square root of mass.
The lattice, the atoms themselves.
So precisely, the frequency of lattice vibrations, how fast the atoms jiggle. Heavier atoms jiggle slower with a frequency proportional to m to the -1/2.
So the critical temperature showed the exact same dependence on atomic mass as the lattice vibration frequency.
That was it. The smoking gun. It was the first direct quantitative link between the macroscopic superconducting behavior, TC, and the microscopic motion of the atoms. It strongly suggested that these lattice vibrations or their quantum packets, phonons, had to be involved.
They had to be the glue.
It certainly looked that way. And it fit perfectly with the theoretical idea from Herbert Froelich around the same time. The pieces started clicking into place.
Okay, phonons. We keep mentioning them. Let's nail down what they are. Quanta of lattice vibrations, like photons for light.
That's a great analogy. Igor Tam and Yakov Frankl came up with the concept, actually. Imagine the crystal lattice, this grid of atoms, isn't rigid. The atoms are connected by bonds, like springs.
Okay.
And they're always vibrating, jiggling around their positions. A phonon is just a single quantized packet of that vibrational energy moving through the crystal, like a tiny ripple of sound or heat.
And these phonons have energy, momentum.
Yep, quantized energy and crystal momentum, just like other quantum particles. And they come in different types depending on how the atoms move relative to each other. Acoustic ones where atoms move together, like sound waves. Optical ones where they move against each other.
Got it. So these tiny jiggles, these phonons, are the key for conventional superconductors. How do they actually make electrons, which hate each other, suddenly pair up?
Right. This is the genius of the BCS theory. Bardeen, Cooper, and Schrieffer, 1957, Nobel Prize stuff.
BCS, heard of it.
It started with Leon Cooper in '56. He asked a crucial question. What happens if you put just two electrons above a sea of other electrons, the Fermi sea, and introduce any kind of attractive force between them, even a ridiculously weak one?
Yeah.
And he found they would always form a bound pair, a Cooper pair. It meant the normal metallic state was inherently unstable if any net attraction existed. The system wants to form pairs.
Okay, so the potential was there. BCS just needed to find the source of the attraction.
Exactly.
Yeah.
And they proposed this beautiful mechanism, virtual phonon exchange.
Virtual phonon exchange. Walk me through it.
Okay, picture an electron whizzing through the lattice. Its negative charge pulls nearby positive ions slightly towards it, creates a little distortion, a region of slightly higher positive charge.
Like a wake.
Sort of. A temporary ripple in the lattice structure. Now that distortion propagates away as a phonon, then a second electron comes along a bit later.
And it feels that leftover positive spot.
Precisely. It gets attracted to that lingering positive polarization created by the first electron. So indirectly, the two electrons have attracted each other, using the lattice distortion, the phonon, as the go-between.
Wow. But wait, wouldn't they still repel each other directly?
Yes, but here's the clever part. The interaction is retarded. The lattice is heavy. It responds much slower than the electrons move. So the first electron is long gone by the time the second electron feels the full effect of the distortion.
The time delay.
That time delay minimizes their direct Coulomb repulsion, allowing the weaker phonon-mediated attraction to actually dominate and bind them together.
That is incredibly elegant. So these are the Cooper pairs.
These are the Cooper pairs, and they have specific properties. They form from electrons with opposite momentum, K and IK, and opposite spin, up and down. So the pair itself has zero total momentum and zero total spin. It's a spin singlet.
Zero spin. So it behaves like a boson, like a particle that can share the same state.
Exactly. Unlike electrons, which are fermions and obey the Pauli exclusion principle, Cooper pairs act like bosons. And what do bosons like to do at low temperatures?
Condense. All pile into the same lowest energy state, like a Bose-Einstein condensate.
Right. Precisely. Below TAC, all these overlapping Cooper pairs, and remember, they're huge, spanning hundreds of nanometers, overlapping with millions of others, they condense into a single macroscopic quantum state, a shared wave function across the whole material.
A giant, coherent quantum wave function made of electron pairs.
That's the ultimate source of zero resistance. The pairs move collectively. And it also explains the Meissner effect. It's this macroscopic quantum coherence.
Okay, my mind is slightly blown. And BCS theory also predicted something called the energy gap, delta.
Yes, the superconducting energy gap. Think of it as the entry fee to break a pair. It's the minimum energy needed to split one Cooper pair back into two individual electron-like excitations called quasiparticles.
And this gap protects the superconducting state.
That's right. Small disturbances like scattering off an impurity or a low-energy thermal phonon, if their energy is less than the gap, less than 2 actually, to create two quasiparticles, they just can't break the pairs. The superfluid of pairs flows right past them, unimpeded. No resistance.
Makes sense. And there's even a prediction for the size of this gap relative to TC.
Yeah, BCS predicted a universal ratio, roughly 2 at zero temperature divided by kBTC, should be around 3.53 for all these conventional weak coupling superconductors. And experiments confirmed this remarkably well for many materials.
Okay, so BCS gave the picture, but how strong is this phonon glue in different materials?
Good question. That's quantified by the electron-phonon coupling constant, lambda. It's a dimensionless number telling you how strongly the electrons interact with the lattice vibrations.
Bigger lambda means stronger glue.
Generally, yes. Stronger coupling usually means a stronger attraction, higher TC, bigger energy gap, although the pairs tend to be a bit smaller, more tightly bound.
And BCS was a weak coupling theory. meaning small lambda.
Right. It worked beautifully for materials like aluminum or tin, where lambda is less than 1. But for materials like lead or niobium, lambda is bigger, the coupling is stronger, and their properties started deviating noticeably from the simple BCS predictions.
So we needed a better theory for those.
Exactly. Enter Migdal-Eliashberg theory. This is the strong coupling extension of BCS. It handles larger lambda values.
How does it differ?
It's mathematically more complex, but the key things are, it uses a frequency-dependent interaction. It doesn't just assume one coupling strength. It looks at which specific phonon frequencies are most effective at pairing the electrons. This is captured in something called the Eliashberg spectral function, alpha power.
Oh, okay, more detailed.
And crucially, it incorporates something called mass renormalization. The electrons get dressed by constantly emitting and reabsorbing virtual phonons. They drag this cloud of vibrations around with them, making them effectively heavier.
Like they're moving through treacle made of phonons.
Kind of, yeah. And this affects their properties.
And the amazing thing is, we can calculate all this now.
That's the really stunning part about the modern state of this field. Using powerful computers and quantum mechanical methods, density functional theory, usually we can calculate a material's electronic structure, its phonon vibrations, predict that crucial function.
And then predict its TC before even making it.
Precisely.
Oh.
And with remarkable accuracy for conventional superconductors. It's truly predictive physics.
You mentioned the hydrides earlier.
Yes, the high-pressure hydrides are the poster child for this. Theory predicted certain hydrogen-rich compounds under immense pressure should have incredibly strong electron-phonon coupling and very high TC.
And experiments confirmed it.
Spectacularly. Materials like lanthanum hydride reach TCs above 250 Kelvin. That's incredibly high, approaching room temperature, although only at millions of atmospheres of pressure.
Still, it proves the phonon mechanism can drive TC very high.
Absolutely. It shows that for these conventional phonon-mediated superconductors, the physics is basically solved. We understand it quantitatively. It's a massive triumph.
Okay, a solved problem, a triumph, but then the plot twist.
Then came 1986, Bednorz and Miller, cuprate.
The high TC ceramics, and everything changed.
Completely shattered the consensus. First, 35 Kelvin and their lanthanum barium copper oxide. Then very quickly, others pushed it way up, like YBCO hitting 93 Kelvin.
93 Kelvin, that's above liquid nitrogen temperature, suddenly much more practical, but also theoretically shocking.
Totally shocking. There was this rough theoretical upper limit, the Macmillan limit, based on phonon physics, maybe around 30 or 40 Kelvin. These new materials just blew past it. It caused a genuine crisis. How is this possible?
Was it just the high temperature, or was there something else fundamentally different?
It was deeper than just the temperature. It was the nature of the superconducting state itself. The symmetry problem.
Symmetry. You mean the energy gap again?
Exactly. Remember how the phonon interaction is pretty isotropic, given that nice uniform swave gap predicted by BCS?
Right. Same everywhere.
Well, experiments on the cuprates, things like angle-resolved photoemission, show the gap was not uniform. It had what's called D-wave symmetry.
D-wave. Like a four-leaf clover shape.
That's a good visual. It means the gap strength is maximum in some directions and goes all the way to 0 in others, the nodes. And crucially, the quantum mechanical phase of the gap changes sign across these nodes. Positive in some lobes, negative in others.
Changes sign. Why is that a problem for phonons?
Because the basic phonon mechanism provides an attractive interaction pretty much everywhere. Can't easily produce a gap that goes to 0 and then flips sign. A sign-changing gap almost always points towards a pairing mechanism that involves repulsion at short distances but can become attractive at others or depends strongly on the direction the electrons are moving.
So the very shape and sign of the gap ruled out the simple phonon picture.
It made it extremely difficult, if not impossible, to explain with phonons alone. It strongly suggested a completely different type of glue was at work.
Okay, so these unconventional superconductors, the cuprates, the iron-based ones that came later, heavy fermions. What ties them together besides just high TC sometimes?
Several common themes or hallmarks emerge. 1. A non-phonic pairing mechanism seems likely, often linked to magnetism or electronic fluctuations.
Magnetism.
Yes, 2. Proximity to magnetism. Very often, these unconventional superconductors appear right on the edge of a magnetically ordered phase, usually antiferromagnetism. You tune the material somehow, pressure, doping suppress the magnetism, and superconductivity pops up. It's too common to be a coincidence.
Interesting. What else?
3. Those anisotropic pairing symmetries, we talked about D wave, maybe P wave, or this plus minuses wave in the iron ones, not the simplest wave. And 4, strong electronic correlations.
Meaning the electrons interact very strongly with each other, not just via phonons.
Exactly. These aren't simple metals where you can kind of treat electrons independently. The electron repulsion is huge and dominates their behavior. They're strongly correlated systems.
Okay, so if phonons aren't the main story here, what is the leading suspect for the glue in these unconventional materials?
That's the multi-billion-dollar question everyone's still racing to answer definitively. The general idea shifted. Maybe any suitable bosonic fluctuation, not just phonons, could mediate pairing. Often, these are collective wiggles of the electrons themselves.
Like what?
Well, the leading candidate, especially for the cuprates and iron-based materials, is magnetic. Spin fluctuation-mediated pairing.
Spin fluctuations,
Yeah.
like magnetic ripples.
Exactly. In these strongly correlated, nearly magnetic materials, even if they don't have long-range magnetic order, there are strong, short-lived fluctuations in the electron spins. Little patches trying to become antiferromagnetic, then dissolving.
Okay.
The idea is that exchanging virtual versions of these spin fluctuations, virtual magnons you could call them, can provide the attractive glue. And because magnetism is inherently directional and related to repulsion, this mechanism naturally produces those anisotropic sign-changing gaps, like D wave or sign.
Does the evidence support this?
There's quite a bit. The proximity to magnetism is key. Also, experiments using neutron scattering see a characteristic spin resonance peak appear only below Tc, which looks like a signature of this pairing mechanism.
Okay, so magnetic fluctuations are one big idea. Any others?
Another intriguing route is more purely electronic, excitonic pairing.
Excitons.
Right.
Those are electron hole pairs, right?
Yes, a bound state of an electron and the absence of an electron, a hole. The idea here is that one electron could interact with another by virtually creating and then destroying an exciton in the material.
So the exciton is the go-between, the boson.
Right. And the big appeal here is that excitons can correspond to much higher energies than phonons.
Meaning potentially much higher TCs.
That's the hope. Maybe even room temperature, if we could engineer materials where this mechanism is strong. People are looking hard at layered materials, like transition metal dichalcogenides, for this.
Fascinating. Any other electronic ideas floating around?
Oh yeah, things like pairing due to electrons hopping between different energy bands or interactions involving correlations across multiple sites. It's a very active area. No single consensus yet for most unconventional superconductors.
Okay, let's try to wrap our heads around this. We have this clear tale of two superconductivities.
Pretty much.
Conventional ones. Mercury, lead, niobium, even those high-pressure hydrides. The hero is the phonon. We get it. We can calculate it. It's a done deal, scientifically speaking.
A solved problem. A real jewel of 20th century physics.
But then, the unconventionals. Cuprates, iron pnictides. The phonon just doesn't seem to be enough. The high TAZ, the weird gap symmetries, the link to magnetism, it points elsewhere.
Right. It forced a revolution.
Yeah.
We're in a new phase, searching for the new rules, the new glue.
Is it possible phonons still play some role even in the unconventionals? You mentioned an isotope effect was seen in some cuprates.
That's a really important point and adds to the complexity.
Yeah.
Yes, a small but definite isotope effect is often seen, suggesting phonons aren't completely irrelevant. Maybe it's an interplay. Perhaps phonons work together with spin fluctuations or modify the interaction. It's likely not always purely one or the other.
So maybe a collaboration of mechanisms.
Could be. And another big idea guiding the search now is quantum criticality.
Quantum critical point, like a tipping point between phases.
Exactly. It turns out the highest TCs are often found when you tune a material right to the edge of another ordered phase, like antiferromagnetism, at absolute zero temperature. Right at that critical point, quantum fluctuations are incredibly strong and long-ranged.
And those fluctuations could be the source of pairing.
That's a very popular and powerful idea. Those intense fluctuations near a quantum critical point might be the cauldron where unconventional superconductivity is forged.
So the ultimate dream is still room temperature superconductivity at normal pressures, right?
Absolutely, that's the holy grail.
And we have these two paths, it seems. The conventional phonon route, which got us high TC, but needs crushing pressures.
Right, amazing science, but maybe not practical for everyday tech.
And the unconventional route trying to engineer magnetism or electronic interactions, which just might get us there at ambient pressure.
That's the gamble. And the potential payoff is enormous. Designing materials atom by atom to harness these exotic quantum effects.
So wrapping up, what does this journey tell us? The phonon. It was the hero, the key that unlocked the first wave of understanding. A massive success.
Definitely. A cornerstone of condensed matter physics.
But its limits forced us to realize the quantum world is even richer and weirder than we thought. And the hunt for the next hero, or maybe heroes of superconductivity, that's where the action is now.
One of the biggest challenges and most exciting frontiers in science, period.
And think about what cracking that code could mean for you, for everyone. Lossless power grids